Hey folks, we're talking today about the second part of the section on sequences. These are really the basic tools we're going to be using from here on in the course. So it may feel like we've walked away from calculus a little bit. We've been spending weeks doing all these integral techniques, and now we're looking at just some list of numbers. And it'll take a while for us actually to connect these ideas back to the things we might think of when we think of calculus, continuous functions and how they behave and derivatives and all those kind of things. But we will. It'll take about 4 weeks. It'll take the rest of the semester. So we're going to have to build up some tools to really understand what's going on. So you can view this as a fun little game, because for a while we're just going to talk about lists of numbers and what happens to those lists of numbers. What happens when you add those lists of numbers together? Do you get a finite value? So this big picture thing, we're going to come back in the end and we're going to use these lists of numbers to actually develop a deeper understanding and a sort of a deeper insight into the functions that we're used to dealing with. And in a sense, in a completely different way of viewing the functions that we're used to dealing with. Okay, back again. You might have heard my timer going off. My tea was ready. I like to let the tea bag be in there for 4 minutes because I'm a little obsessive compulsive. But anyway, back to limits of sequences. Here's an example. We'll start with an example of one of these objects that we kind of talked about last time. So this is an example of an important type of sequence. And if you look at that and you remember the kind of notation we introduced last time, I could write that as 1/3 to increasing powers, so to the power n, starting at 1. Well, in fact, not starting at 1, starting at 0 in this case, because this first number is 1/3 to the power of 0. And then this is 1/3 to the power of 1, 1/3 squared, right? Because those values in the sequence are literally the powers of 1/3. 1/3 to the 0, 1/3 to the 1, 1/3 squared is a 9th, 1/3 cubed is a 27th, and so on. And this ... remember, means that this pattern continues forever. So what we're saying is the general term here is 1/3 to the power of n, and in fact we want n bigger than or equal to 0 in this case. So this is an example of what's called a geometric sequence. And we'll see these kind of things come up again and again. These are the kind of problems we're going to be interested in a lot. We're going to see these geometric sequences reappear. And in general, for a geometric sequence, the nth term is going to be r times some, not times, but r raised to some power, where n is bigger than or equal to 0. So this is the general form for a geometric sequence. In this case, r is 1/3. And just for sort of generality, I'm going to put a c out the front, and c is just a constant, right? So we've got a constant c, and we've got a value of r is also a constant, but it's greater than 0. So in our example, r was 1/3. And this is what I'm going to refer to from now on as a geometric sequence. So in this example that I gave us here, that's our general term. C is 1 and r is 1/3. So we have this nice geometric sequence. And going back to the general case, we see the limit of this thing. The limit as n tends to infinity. You think about what's happening, these numbers are getting smaller and smaller, right? The denominator here is just going to get larger and larger and larger. The numerator is fixed, it's just 1. And so this limit is going to be 0. It's a weird shape, 0. And so the limit of this sequence is 0. And so the sequence converges. We say the sequence converges to 0. And there we go, that's about what we can talk about. So the sequence here converges to 0. In general, you can kind of think about what would happen in cases like this. Here's another example of a geometric sequence. And if you look at that for a moment, you can say, okay, this is starting with a value of 3, and then I'm multiplying it by 2 each time. So I can think about that as 3 times 2 to the 0. The next one is 3 times 2, which is 6. The next one is 3 times 2 squared, which is 12. The next one is 3 times 2 cubed, which is hopefully 24. The next one's going to be 48, and so on. Right, so this is another geometric sequence. And the key property with the geometric sequence, you can see it here, each term appears from the previous by being multiplied by a constant factor. That's the thing that makes it geometric. So each time I go from one term to the next term, I'm multiplying it by a constant factor. And that constant factor is the r value, right? I go from here to here by multiplying by 2, there to there by multiplying by 2, there to there by multiplying by 2. Up here, I went from one term to the next by multiplying by 1/3. So the r value was 1/3. Where did I write it? R is 1/3. So in this case, down the bottom, our bottom example, the R value must be 2 because we double term to term. So this is 2 to the 0, 2 to the 1, 2 to the 2, right? And it's always R that's raised to that power. And C is just a constant out the front that I can factor out. And you can see I've essentially factored out a 3 here. So this is a geometric sequence with R is equal to 2 and C is equal to 3. What do you reckon the limit will be here? What's the limit for this sequence? I'll just squeeze it on the bottom. What's the limit as n tends to infinity for this, right? Remember, that's the limit as n tends to infinity of 3 times 2 to the power of n. And those numbers are just getting bigger and bigger and bigger, and so it diverges, right? The limit here will diverge. The sequence will diverge. The numbers are just going to get bigger and bigger. 24, 48, what's next? 96, and so on. It's just going to keep doubling forever. It's going to diverge to infinity. So these sequences give you an idea of how these limits work. Let's kind of summarize what I've talked about here. And in fact, hopefully you can see from these examples that if the value of R is less than 1, this thing's going to converge, because when I take a number that's smaller than 1 and I square it, or I multiply it by itself, every time you multiply it by itself, you're going to get a number that's smaller than the one you had, right? Because you've got some value and you multiply it by a number less than 1, so what you're left with is something that's smaller. So each term is going to be the smaller than the one that came before. But if R is bigger than 1, even if R is like 1.01, then when you multiply 1.01 by 1.01, you get something that's a little bit bigger than 1.01. Because you get one lot of it plus something else, right? Literally, you're multiplying by this quantity. You're multiplying by 1 plus 0.01. So when you take your old value, right, your R squared, well, that's 1.01 times R, because I'm imagining R is 1.01. And so this is 1 plus 0.01 times R. So this is R plus 0.01 times R, so it's your old value plus a little bit. So as long as R is bigger than 1, you're going to get a value that's bigger than you had, bigger than the R you had. And so if R is bigger than 1, it's going to diverge. The values are just going to get bigger and bigger and bigger. If R is smaller than 1, but still positive, because we're not going to be interested so much in what happens when it's negative, but if it's right now anyway, but if it's positive, then it's certainly going to converge. And in fact, you could take this further. Here's a general statement of what I just said. You could take this further, and you could actually say that these geometric sequences will converge if the absolute value is less than 1, and it'll diverge if the absolute value is less than 1. Because you imagine you get minus a half and you multiply it by minus a half, well, you've got a number that's smaller in absolute value, so it'll converge. And in fact, it'll converge to 0, right? So I can add to this. So when I take the limit for a geometric sequence, what I'm going to get is a number that converges to 0 if the absolute value of R is less than 1, and it's going to diverge if the absolute value of R is bigger than 1. And so that's geometric sequences. Let's have a look at another useful idea, and that's the squeeze theorem for sequences. You may remember that we had squeeze theorems in Calc 1. We said that if two functions have a limit and that limit agrees, and I've got another function that's stuck between those two, then it's kind of, you're forced to have the same limit for all three functions. Here's the kind of idea we had. If we have a function, I'm calling it g here, and it's trapped between two other functions, and the two other functions are f and h, and f and h are both approaching the same limit. If f and h are both approaching L, in the long term, the idea is that these curves are settling down towards the number L. I don't know if I can try and draw those curves. Those curves are both settling down towards the limit L, and g is always trapped between them, then g must also settle down to the limit L. So it said, in fact, that the limit of g must be equal to the limit of f and h, and they were both L. And so this theorem for sequences says the same thing. Because remember, you can think about sequences maybe as being points on a function. So we're saying if I have a bunch of points, and those points are such that these points that I'm drawing here are the values of c sub n, and then I have some points here, and I'm going to call these points a sub n. If I have this list of values, that's what a sequence is, it's just a list of values. Well, sorry, I'm going to call that b. If this is b sub n, then if these other values a sub n, here they are, the a sub n are on this curve in the middle. If a sub n, if the value for that is always tracked between the other two curves, well, not curves, the other two sets of points, there's our a sub n, and those two separate sequences, b sub n and c sub n, have the same limit, then the limit of a must be that as well. And that's kind of a useful idea, and we saw in Calc 1 why it's useful. Let's do an example where we see it here. Here's an example that uses the squeeze theorem, and the hint here that this sequence, and think about what the sequence would be, it's useful to start writing these things out. Cosine of 1 over e, we're going to get a bunch of values, and I don't know what these values are in terms of exact numerical values. You can get a calculator and you can work out the cosine of 4 and divide it by e to the 4, but the point here is that we want to know what happens in the long run. So does it converge or does it diverge? And you might look at this and think, well, cosine doesn't grow real fast, but exponential does, so it converges. And the squeeze theorem gives us a way to really argue that. Because what you can do is say that I know that the cosine of n is greater than or equal to 1 and less than 1, right? Because that's the range of the cosine function. Cosine always gives a value between minus 1 and 1. And it doesn't matter that I'm plugging integers in, this n thing is an integer. So I could divide that whole thing by a positive number, and the positive number I'm going to divide by is e to the power of n. Why am I doing that? Because that gives me the function I want in the middle here. So then I can take advantage of the squeeze theorem, because the squeeze theorem says if I can squeeze the thing I'm interested in between two other sequences, and those two sequences have the same limit, then the limit of the one I'm interested in will also be the same as the other two. So here I've built the inequality. Your job with these squeeze theorems is to build an inequality. And this inequality is going to be true, in this case, for all n greater than or equal to, well, it would work for 0 maybe, but yeah, I mean, it would work for 0. I started my sequence at 1, so let's just say 1. The point with the squeeze theorem is it only has to be true for eventually. It doesn't matter if it's not true for a couple of terms, because we're looking at what happens a long way down the sequence. Right, we're looking at values when n is really large. So two things we need to know before we can take the squeeze theorem and use it are these two limits. They have to be the same for the squeeze theorem to be useful. And if you think about the exponential increasing, it's going to infinity, it's in the denominator, so those two things must be 0. And so what we've got is we've set up this sequence that we're interested in to be trapped between two other sequences that we can take the limit of. And because we've satisfied all the conditions here, the sequence we're interested in with the cosine, it lives between those two purely exponential ones. We understand what happens to exponential functions as n goes to infinity, so we can conclude that those limits are the same. Both of those things are 0. That's our L in the theorem. And that tells us, therefore, that the limit of the cosine is also cosine over e to the n. That sequence is also 0. Wasn't that fun? Let's have a look at another. All right, so let's look at this example, and this is kind of a fun one. If you haven't seen this n factorial before, n factorial is called the factorial function. Well, it's not a function. It's just called a factorial. So n factorial is the product of all the integers from 1 to n. So 1 factorial is just 1, and 2 factorial is just 1 times 2. And 3 factorial is 1 times 2 times 3. And 4 factorial is, I think you get the idea, right? Times 4. And then the n factorial, we could write it kind of formally. N factorial is just going to be 1 times 2 times 3. All of the integers multiplied together up to n minus 1 and then n. So all of them multiplied together. That's all the factorial is. So 0 factorial, we just define it to be 1. So just for fun, this really makes no sense, but it's useful in our formulas to have an understanding of what 0 factorial is. It's just 1, but it's defined for all positive integers. So for all integers n bigger than or equal to 1. But I'm going to expand it to all integers bigger than or equal to 0 by just adding this definition. All right, so with that understanding, let's go back. So a1 here is just going to be 1 over 1 to the power of 1. And so the second term is going to be 1 times 2, that's 2 factorial. Right, let me write that out. This is 2 factorial over 2 squared, so this is 1 times 2. It sometimes helps just to write that 1 times 2 there. And we know what 2 squared is, I'm just going to write it that way. And a3, that's going to be 3 factorial over, well, this is going to be, what is it, 2 cubed. No, I'm sorry, 3 cubed. 3 cubed. And so that's going to be 1 times 2 times 3. And that's going to be divided by 3 times 3 times 3. I'm just writing this out to get a feel for what's going on. 4 factorial over 4 to the power of 4. So this is 1 times 2 times 3 over 4 times 4. I think I missed a term. Times 4 times 4. All right. So there's our, really ugly, there's our first 4 terms. And what we're going to do here is use the squeeze theorem to work out the limit. So the limit as n tends to infinity. And we can't really use any of our tricks and techniques of thinking about this as a function, because there's no such thing as x factorial. I could write x to the power of x up here and use L'Hopital's rule and that kind of thing, but I can't look at the limit as x goes to infinity and think about continuous functions like I did last time to do the limit, because these are discrete numbers and there's no such function as x factorial, right? At least not that we've met. But for now, let's just think about rearranging some of this. And what I'm going to do is factor out kind of the leading term in each of these. I'm going to pull it apart from the rest. And I did that, and I added the general term here as well. Right? The general case, we can always do this. And the reason we can do it is the number of terms here match up. If you look at the numerator in this example, there's 4 numbers. If you look at the denominator here, there's 4 numbers. So each of these matches up. And each of them is actually, each of those, if I think about matching them up, each of them is going to give a number that's less than or equal to 1. N is some number that you stop at, right? So the last, let's look at this one. 2 over 3, well that's less than 1. 3 over 3, that's equal to 1. So when I multiply those two numbers together, I get something that's less than or equal to 1. This is just equal to 1. Right, when I do it here, 2 over 4, that's less than 1. 3 over 4, that's less than 1. 4 over 4, that's equal to 1. When I multiply them all together, I get some number in this collection, or I get some number, but what I know about it is that it's less than 1. Because the largest value here is going to be the same as the number in the denominator, so that last term is always going to be 1. Here's the last term. Here's the last term. Here's the last term. Here's the last term. Let's go back to red because red was fun. Here's the last term. That last term is always going to be less than, that last term is always going to be equal to 1. And all of the others are going to be less than 1. And so when you multiply them all together, what you're going to get is some value that's less than 1 here. And I've got a quarter there. So this is less than 1/4 because this is a quarter multiplied by something that's less than 1. So I get something that's less than a quarter. This is less than a third because I get a third and I multiply it by a number that's less than 1. This is less than a half. Well, actually it's not. It's less than or equal to a half. In this case, it's actually equal to a half. So just to be fair, I'm going to put an equal there just in case that happens, because it happens here too. I can write that as 1 over 1, and that's definitely less than or equal to 1 over 1, right? Because it is 1, so it's equal. And in this general term, I can say this is less than 1 over n. Because all of these values are less than or equal to 1, so the product of them is going to give a number that's, well, it's going to give a number that's less than n for all n that are bigger than 2. But in general, we can just say it's less than or equal to n. But hang on, now we've got some nice statement about a sequence. We know that a sub n, which is what we're interested in, is less than or equal to this. And I know it's always positive. These numbers are always going to be positive. So I can say here that in fact this term that I'm interested in, n factorial divided by n to the power of n, it's always less than or equal to 1 over n. And in fact it's always greater than or equal to 0. So what I've done is set up an equality that looks like that. Well, this is true for all n bigger than or equal to 1. Because look, we did it at 1, we did it at 2, we did it at 3, we thought about the general case. So this quantity is less than or equal to 0, and it's greater than or equal to 0, and it's less than or equal to 1 over n. And so what we found is that the term we're interested in, n factorial over n to the power of n, it lies between these two other sequences. So let me ask you, what's the limit as n goes to infinity of 1 over n? Well, that's a Calc 1 problem. We know the answer of that. It's 0. What's the limit as n goes to infinity of 0? So what I'm doing here is I'm looking at this limit and that limit. And we know the limit as n goes to infinity of 0. It's 0 because the thing's always 0. And so we've shown that the term we're interested in is trapped between two other sequences. The two other sequences both have the same limit. That limit is 0. And so we can conclude that this term that we're interested in must also go to 0 because it's trapped between the other two values, the other two sequences, 1 over n and 0. It's always less than 1, whatever the terms in this sequence. Let me be careful here. The nth term in the sequence we're interested in is always less than the nth term in this sequence, but bigger than the nth term in that sequence, or equal. And these two sequences both converge to 0. And so by the squeeze theorem, this sequence we're interested in also converges to 0. Okay, so that's how we can use the squeeze theorem. Not everything is going to be something we can turn into a differentiable function. So we're going to have to use this idea sometimes. Let's look at some more ideas of convergence for these sequences. All right, so I want to finish today by talking about a few terms that we'll use going forward. And one idea that's important is the idea of bounded sequences. And bounded is exactly what it sounds like. A sequence is bounded if you can put bounds on it. So that doesn't help you at all, right? Imagine I've got some number m, big M, and some number small m down here, and then I've got values for a sequence. And here are my values for the sequence, right? And the sequence is only defined at the integers, so it's not a curve, it's just some bunch of points. But imagine my sequence somehow looks like this. Then what I can say about that sequence is that it's bounded above by m, which just means that all of the terms in the sequence stay smaller than, or at worst equal to, big M, and it's bounded below by small m, because all of the terms in the sequence stay below that line, y equals small m. And so that's why we call small m a lower bound and big M an upper bound, because one of them's above the sequence and one's below the sequence. And if you have a sequence like the one I've drawn that has an upper bound and a lower bound, then we just say it's bounded, which means above and below. So the two together means a bounded sequence. If it's not bounded, then it's unbounded. So for example, the sequence we thought about before, which was 3 to the power of 2n, that sequence, remember, was it diverged to infinity. Remember, the sequence in that case had terms that just got bigger and bigger and bigger without bounds. So if I sort of sketch the terms are going to look like there's going to be a 3 and then a 6 and then a... So these are getting bigger without bound. In other words, I could never find an upper bound. There's no value of big M where those green dots will stay below it. No matter how big that is, I'll always eventually cross that term. So a divergent sequence is by nature unbounded. Well, something that diverges to infinity, I should say. So in this case, the limit as n goes to infinity for this sequence, yes, that's right, was infinite. And so a sequence that diverges to infinity is going to be unbounded, or diverges to minus infinity is going to be unbounded. And here's kind of an example from the book that shows you. Obviously, in my first example, that big M that I drew, it wasn't the biggest, smallest upper bound that you could draw. I could have drawn a different M. Maybe that's M1, I could have called M2. M2 is also an upper bound, right? So there's often a smallest upper bound. So the smallest upper bound I could draw is the one that went straight through that line, right? The one that went straight through that point, because the value is allowed to equal M, but it's never allowed to be bigger. So this one that I've drawn here, that's the smallest possible upper bound. So you can choose different upper bounds, which this kind of picture is getting at. And we could do the same thing for lower bounds. So on this picture, the lower bound that just touches that point would be the largest lower bound that we could choose. All right, let's think a bit more about this. I said that if a sequence goes off to infinity, then it's unbounded. What happens if it converges? Well, here's a nice little picture I stole from the book that kind of visualizes the terms in a different way. This is just the number line, and it's just drawing the values of A on the number line. So there's the first value of A, there's the next value of A, there's the next value of A. And you can see they're stacking up towards this value L. They're approaching the limit L. If I draw it in our normal way, then we're looking like this. So it's stacking up in the y direction, because what we're seeing here, they've called it x, but I'm really going to call it a sub n. It's really this axis. So there's a1, there's a2, there's a3, there's a4, there's a5, there's a6. So that's what they're sort of visualizing here. And you can see that here's the smallest value. So this could be used as a lower bound. The lower bound here is a1 perhaps. And it's approaching this limit L, and it's increasing each time, and so L is an upper bound. But so is big M, right? It's bigger than L, so it's an upper bound too. And so this kind of leads us to the following theorem. And it's a very straightforward theorem. It says that sequences which converge are bounded. And you can see that this convergent theorem, this is a sequence. This sequence is increasing, but it's convergent. It's approaching L. It's increasing the whole time, but it never crosses L. And so it's definitely bounded. And this is true in general. Any sequence which is convergent will be bounded. Because imagine what unbounded means: the thing goes off to infinity or negative infinity. And if it does that, then it's not convergent. So therefore a convergent sequence must be bounded. And this example here leads to another kind of theorem as well. And it says that if you've got an increasing sequence which is bounded above, so this is this exact case, the values are increasing, but it's got an upper bound, then it must converge, right? Now I've turned the statement around. Now I'm saying if it's increasing and it has an upper bound, then it has to converge. And that limit has to be less than or equal to M, right? Because I might have put my M, oops, that's a terrible line. I might have put my M here. So all of the points on this sequence are less than M, and it's increasing. And so it's got to converge somewhere, but it might converge to something lower than M. It might converge to this line out. And similarly, if it's a decreasing sequence, but it's always bigger than some value, in other words, it has a lower bound, it's bounded below, here's our lower bound, then I've got some values that are decreasing over time, or over values of n, but they never cross M, then it must have a limit, and that limit, in other words, it must be convergent, and that limit is M at the smallest, maybe bigger than M. So let's see an example of that. So here's a sequence. I want to show it converges. And I'm going to use some of the tricks to do with the log laws. And then I'm going to use this theorem down here, theorem 6, to say that I've got an increasing and bounded function which converges, or a decreasing and bounded function which converges. So to begin with, I'm just going to rewrite this a little bit using the log laws. And in fact, I'm rewriting it in a maybe a little non-obvious way, and that's because it's going to help me. But the fact that you wouldn't guess this is perfectly okay. But the idea is I've created a term on the top which is equal to the denominator. So this is 2n over 2, that's just n, right? But then I can split it using the log laws, and then I can just divide. Log 2n over log 2n, that's 1. And then I'm going to subtract the natural log of 2 over the natural log of 2n. So I've rewritten the terms a bit more simply. And in fact, we know that n is bigger than or equal to 1. That tells us that log of 2n is going to be positive, right? Log of 2n is going to be positive, and also log of 2 is positive. And think about the graph. The log function looks like this. Oops, not like that. That's a terrible log function. The log function looks like this when you plug, if this is a log of, well, let's call that x. If this is a graph of the log of x, when you plug in a value that's bigger than 1, then you're going to get a positive number, right? A positive number coming out. And if n is at least 1, then 2n has got to be bigger than or equal to 2, in fact. So I'm plugging in numbers bigger than 1 here. This is bigger than 1. So the log function is going to be positive. So the whole point of that argument is that this value here, this is positive. Right? So notice what that tells me immediately. If I'm taking 1 and I'm subtracting a positive number, the an value is less than or equal to 1. So it's bounded above. Right, another way to put it, a sub n is bounded above. It's bounded above by 1. And for the same argument, if n is greater than or equal to 1, then all of these values are going to be positive. Log n is at worst going to be 0 and then positive. So this thing is actually bounded below is bounded below as well. So the values in this sequence are going to be greater than or equal to 0 and less than or equal to 1. And so it's bounded. And bounded sequences converge, right? Convergent, no, that's not right. If bounded sequences converge, we can make that conclusion if we can also determine if it's increasing or decreasing. Why would that be, by the way? Get rid of that. Let's think about this theorem. It says bounded sequences converge, right? If it's increasing and it's bounded above, it converges. If it's decreasing and it's bounded below, it converges. Why doesn't it just say every bounded sequence converges? well, here's a bounded sequence, and this bounded sequence that I'm drawing, the idea here is it's going to bounce around forever between those two values. Maybe it's just a sine curve, right? Maybe I'm just drawing a sine curve. But this doesn't converge. This doesn't converge, so it must diverge. The sequence I've drawn here diverges, even though it's bounded. Right? It's bounded above, it's bounded below. It could just be a sine or cosine function here. But the idea is I can oscillate forever, and so it never settles down to a limit, and so the limit doesn't exist, and so the sequence diverges even though it's bounded. So diverging doesn't mean goes to infinity necessarily. Back to our example, we have something that's bounded between 0 and 1. Let's look at the function. If a sub n is the function that we're dealing with here, it was 1 minus the natural log of 2 over the natural log of 2n. I can go back to that theorem we had last time and define, well, and think about the function that's generating this sequence and think about it as a function of continuous variables. And we had a theorem that says the limit of this function will equal the limit of this sequence. And so let's find the limit, not the limit. I'm going to look at whether this is increasing or decreasing. I'm lying. I'm going to ask whether this is increasing or decreasing because this is the function that generates the sequence. And so if I know if this is increasing or decreasing, I know whether the sequence is. We know how to find increase and decrease. We look at the derivative, right? The derivative is always positive, it's decreasing. Sorry, it's increasing. If it's always negative, then the function's decreasing. And so just log 2 is a constant, so differentiating this, I'm bringing the minus power down, creating a positive, and then increasing the power by 1, and then I'm differentiating all of this here. Sorry, I didn't put the derivative sign. So it's just the chain rule. This is constant over u, and so the derivative is, well, minus constant over u. The derivative is positive constant over u squared times the derivative of u. And if you work that out, that's 1 over x. This is definitely positive because it's being squared. X is greater than 0 because we're only interested in values. Remember, this sequence is being defined by this thing. It's given by the values of this function for n bigger than or equal to 1. And so n's bigger than or equal to 1, so x is bigger than or equal to 1, right? Really what I'm saying is x bigger than 1, but it's actually positive therefore. And so this whole thing's positive. Log 2 is positive, 1 over x is positive, this square is positive. So f is an increasing function. And it's an increasing function for all x greater than 0, but more importantly, it's increasing for all x greater than or equal to 1, and that lets us conclude that a sub n is a bounded function. Remember, it's greater than or equal to 0 and less than or equal to 1. And it's an increasing function, and that means that the sequence is convergent. The sequence converges to a value, and I know that because the sequence doesn't get bigger than 1, the limit is less than or equal to 1. I don't know what it is, but it's going to be less than or equal to 1. And that's coming from our theorem, because our theorem says if it's increasing and bounded above, which it was, it's less than or equal to 1, that means the limit is also bounded above. So that sort of hopefully gives you more feeling for these sequences. And we're looking at sort of complicated ideas and defining the limits, but it's these ideas are bounded and things you'll get used to as you work with them. So have a go at some problems, the web work, and come see me in office hours. I hope to talk to you soon. Ciao.